Here goes section 2.1, using inductive reasoning to make conjectures. Our objectives: I can use inductive reasoning to identify patterns and make conjectures. I can find counterexamples to disprove conjectures. Sounds like we're going to need to know a couple vocab words: inductive reasoning, conjecture, counterexample. All three of those things we saw in our I can statement. So first thing we're going to do is look at some patterns. January, March, May. You probably know just from looking at this we're skipping 1 month every time. So we're alternating months to make up the pattern, which means our next month is July. Here, of course, we're adding 7 every time. That's pretty easy to see, which means our next multiple is 35. You're going to see a couple of things like this. Think about this one. What are we doing to this one every time? What should the next figure look like? We're rotating it here. So we're rotating it counterclockwise, which would be this way. We're rotating counterclockwise. So we rotate it one more time, and we've got the point pointing off to the right. And I think I'm in a mirror, so I think it goes that way. But our figure is going to the right there. Here, what's our pattern? Oh, we don't have to get technical about it. We're just adding another 0 on the inside after the decimal each time. So we're getting one more 0. So the whole point behind this is what you do, how you're solving those patterns. That is called inductive reasoning. When we are looking at specific examples, we're looking at the pattern that they form and assuming that the pattern is going to continue. That is inductive reasoning. So this is basically saying that a rule has to be true or a statement has to be true because of what we've seen in the past, because of the specific cases that we've seen in the past. So all of those patterns that we did, that was inductive reasoning because we used what we saw in the past and we assumed that the pattern will continue. That is inductive reasoning. So the statement we believe to be true based on inductive reasoning is called a conjecture. It's like a theory. It's because of everything that I've seen, this is what I believe to be true. That is our conjecture. So we're going to take a look at some conjectures here. First one, the sum of two positive numbers is blank. Well, how we're going to come up with this is we need to find those specific examples. So, we start adding two positive numbers and seeing what it equals. If we do that, 1 plus 1 is 2. They got a couple other examples there. If we're adding two positive numbers together, our answer is always positive. That's what they're looking for. Is what do they have in common? Well, they're always positive here, so that would be our conjecture. The sum of two positive numbers is positive. The next one, product of two odd numbers. Why don't you try it out? Okay, pause it, multiply a couple odd numbers together, see what the pattern is, see what it always equals. Come on back, see if you got it right. Okay, so when we look at this, if we try some examples, 1 times 1, 3 times 3, 5 times 7, all those answers have something in common. They're all odd. So that's our conjectures. The product of two odd numbers is odd. So if we look at data tables, we can use conjectures in data tables as well. This would be a biology application, something that scientists would do. So if we're looking at the height of the whale's blowhole or the water coming out of it, you see the data in the chart. If we wanted to make a conjecture about that, well, there's a couple different things we could say. Obviously, the height of the blue whale blows are higher than the height of the humpback whale blows. So there's our conjecture right there, is that the height of the blue whale is bigger than the height of the humpback whale. We could also be more specific and say it's about 3 times greater. Either one's going to be fine, but that is our conjecture. So you see our two possible conjectures there. So I want you to come up with a conjecture here about the length of a male and female whale based on this data. Come up with a conjecture, see if I came up with the same thing here. Alright, so when we do that, we notice that most of the time the female is longer than the male. So our conjecture is that female whales are longer than male whales. Alright, so just a basic conjecture based on the evidence that we've seen, based on the specific cases that we looked at, that's using inductive reasoning. So to prove that conjecture is true, you must prove it, but to show that it's false, you need one example, just one example showing that it doesn't work. That's called a counterexample. So if you're going to prove something false, you need just one example that shows it does not work. That's your counterexample. It could be a drawing, could be a statement, or a number, depending on the type of problem you have. So if we're looking at this, for every integer n to the third is positive. So whenever you're finding a counterexample, the first part of the statement has to be true, and then the second part of the statement has to be false. So the first part of the statement is for every integer n, which means n has to be an integer. And then for this to be a true counterexample, a good counterexample means that the second part is going to be false. So we have an integer n, but n to the third power can't be positive for our counterexample. So we can just try different integers. It's basically guess and test until you find one that makes this false. And so 1 works. Okay, n to the third is 1, so 1 is greater than 1, which is positive. So that works, so that can't be it. But if we make it a negative, if n is negative 3 is still an integer, but negative 3 to the third power is negative 27. Well, that's not positive, so that makes our conjecture false. That is our counterexample, negative 3. I want you to think about this one now. Okay, I want you to pause it, think about it, come on back. Two complementary angles are not congruent. Give me a counterexample. Okay, so the only counterexample that we could have are two 45-degree angles, because if we have complementary angles that are congruent, so the first part has to be true, two complementary angles, the second part has to be false. So instead of not congruent, they are congruent, so our counterexample would be 45 degrees and 45 degrees. Okay, again, pause it, try it, come on back. Okay, so the conjecture is false by finding a counterexample. So it has to be a real number x, which basically any number you can think of is a real number. But the second part has to be false. X squared cannot be greater than or equal to x, which means x squared has to be less than x. So the only way this is going to work is if we have a decimal or a fraction. It's got to be between 0 and 1. There's our counterexample. Because if we do 1/2 squared, that gives us 1/4 or 0.25, which is not greater than or equal to 1/2. So there is our conjecture is false, and our counterexample is 1/2. Okay, here's your quiz. I want you to pause it, try it, come on back, see if you got the right thing. Alright, so for number 1, we've got 3 zeros on the inside there. For number 2, we've got an arrow pointing straight up. We are rotating that clockwise 90 degrees every time. For 3, that is true. Okay, quotient of two negative numbers is a positive number. Negative divided by negative is always a positive. Every prime number is odd. There's false. There's your counterexample. The number 2 is prime. So that is a false statement with our counterexample. Two supplementary angles are not congruent, 90 and 90, just like the complementary one we talked about. And then the square of an odd integer is odd. So if we take an odd integer and we square it, it will be odd as well. So 9 times 9 is 81, 3 times 3 is 9, so on. So that is true. That's it for 2.1, inductive reasoning and conjectures and counterexamples. Make sure that you're looking over this. You got a good solid base on inductive reasoning before we move on to our next type of reasoning, which is deductive. So make sure that you understand that it is specific cases that we can take and form a rule off of those specific cases. That's it for section 2.1.